Welcome to today's class. In today's class, we discuss about the queuing model. So, from this concept, a student can learn what is actually queuing model, the different characteristics of a queuing model, different notations and symbols used in queuing model, the statistical methods of queuing, decision problems in queuing, and various problems. Now we discuss about what is actually queuing theory and queuing model. Before we discuss about the queuing theory, it is very essential to know the two things, that is why the queue occurs. When the customers standing near a server or service point for their turn, and at the service point the server gives the service with a particular time. If that time is greater than the customer's arrival time, then the queue occurs. So queuing theory is a branch of mathematics that studies how lines form, how they function, and why they malfunction. Queuing theory examines every component of waiting in line, including the arrival process and the number of customers among others, which might be people, data packets, cars, or anything else. Means a customer standing in a queue for their turn to get the service from the service point, or sometimes the vehicles are standing near the garage for their turn to get the service from the mechanics. A real-time application of queuing theory cover a wide range of business. Its finding may be used to provide faster customer service, increase traffic flow, improve order shipments from a warehouse, or design data networks and call center. Once again, what is actually queuing theory? Queuing theory deals with problems which involves queuing or waiting. Before going to queuing theory, one has to understand the two things in clear. That is, one is service, another is your customer or elements. Here, customers or elements represents a person or machine or any other things which is in need of some service from servicing point. Service represents any type of attention to the customer to satisfy his need. Then how queuing theory works? Queuing theory aims to design balance systems that serve customers quickly, efficiently, but do not cost too much to be sustainable. As a branch of operation research, queuing theory can help inform business decisions on how to build more efficient and cost-effective workflow systems. Queues can occur whenever resources are limited. For example, suppose there is one service point, that is means one server where the customers get the service. If one service point is there and number of customers are more, then at that time the queue will occur. Some queuing is tolerable in any business since a total absence of a queue would suggest a costly overcapacity. Queuing theory as an operation management technique is commonly used to determine and streamline staffing needs. Suppose there are number of customers, more customers are there, and one servicing point is there to take the service. At that time, we need to streamline how to give the service to their customers. So staffing needs. And we prepare the scheduling also and inventory in order to improve overall customer service. Then application of queuing theory. The queuing theory can be used and applied in a number of different situations. For instance, it can be applied to business logistics, banking and finance, telecommunication, project management, emergency service such as fire, police and ambulance. How it works and how involved it may be depends on the complexity of the case involved. Then what are the parameters of the queuing theory? There are different parameters. Means these are the requirement words we can use in our queuing model or queuing theory. What is arrival? Arrival refers to the customer who arrive and are first in line. Means if there is a one service point, at that time the customers arrive in different times and to take their service. If one service point is there and more than one customers are standing for their turn, then a queue forms. That is known as the arrival of customer. Queue or service capacity refers to the limits of the system as per the number of customers in line. Then number of servers refers to the total number of employees serving the customers in line. Suppose in a bank there are two counters for deposit the checks. Means there are two servers. That is known as the number of servers. And number of queues also occurs. Size of the client population refers to the total number of customers in the line. That means in a line how many customers are there and waiting for their turn. Queuing discipline, it is very important, refers to how requests are delivered to the server. That means we may consider also fast in, fast out, last in, fast out in this way. Then departure process refers to customers leaving after receiving service. So these are the different parameters of queuing theory. Examples of queuing theory. Persons going to hospital to get medical advice from the doctor is an element or a customer. A person going to railway station or bus station to purchase a ticket for the journey is a customer or an element. A person at ticket counter of a cinema hall is an element or a customer. A person at a grocery shop to purchase consumable is an element or a customer. A bank passbook tendered to a bank clerk for withdrawal of money is an element or a customer. The machine breakdown and waiting for the attention of a maintenance crew is an element or a customer. Vehicle waiting at traffic signals are elements or customers. A train waiting at outer signal for green signal is an element or a customer. So these are the different examples of the queuing theory. Then different notation and symbols of queuing system. Small n indicates the number of customers per units in the system. Means if number of people are standing in a queue for their turn or to take their service from the server, that is known as n, number of customers per unit in the system. Then Pn of t, that is tangent state probability, that exactly. Similarly, P of n equal to steady state probability of having n units in the system. Then lambda n indicates average number of customers arriving per unit of time. Means a particular period of time, how many customers arriving, that is known as the average number of customers. When there are already n units in the system. Lambda equal to average arrival rate when lambda n is constant for all n. Mu n equal to average number of customers being served per unit of time when there are already n units in the system. Mu equal to average service rate when mu n is constant for all n greater than or equal to 1. S equal to number of parallel service channels in the system. So these are the symbols we are used for the solving of queuing problem. 1 by lambda equal to inter-arrival time between two arrivals. Hence we have to find the interval time between two customers' arrival. 1 by mu equal to service time between two units or customers. Then capital N equal to maximum number of customers allowed in the system. LS average number of customers in the system. LQ average number of customers in the queue. WS indicates average waiting time in the system. WQ average waiting time in the queue. Then P of W equal to probability of a customer having to wait for service. Then we discuss about queuing model and classification. Once again, I am explain a common situation occurring in everyday life is that of queuing or waiting in a line. Queues form at bus stops, ticket counters, doctors, and clinics, a bank. Everywhere there must be a queue we are facing in our everyday life. In general, queue is formed when either units require service, refer as customers, wait for service, or service facilities stand idle and wait for customers. So that is known as actually the queuing theory. Queuing theory can be applied to a wide variety of operational situations where imperfect matching between the customers and service facilities is caused by one's inability to predict accurately the arrival and service times of the customer. In particular, it can be used to determine the level of service that balance the following two conflicts of cost. Cost of offering the service and cost incurred due to delay in offering service. So this is known as actually what is actually the queue. Now we discuss about the queuing model and its classification. Most elementary queuing models assume that the inputs, arrivals, and outputs temperature. Input is always arrival, customer arrival, and output means the customer takes their service and temperature. Follow a birth and death process. Any queuing model is characterized by situations where both arrivals and departures take place simultaneously. Depending upon the nature of inputs and service facilities, there can be a number of queuing model as below. Number one, probabilistic queuing model. Both arrival and service rates are some unknown random variables. Then deterministic queuing model, both arrival and service rates are known and fixed. Then mixed queuing model, either of the arrival and service rates is unknown, random variable, and other known and fixed. Then queuing process. A queuing system can be completely described by the input, that is called the arrival pattern, how the customers visit to the server, a service point, the service mechanism or service pattern, the queue discipline, and customer behavior. So components of the queuing system are arrival, the element waiting in the queue, the unit being served, the service facility, and the unit leaving the queue after service. So, we can discuss what is actually input process. The input process means the input describes the way in which the customers arrived and joined the system. Means a customer arrived and join the system is join in the queue to take their turn. In general, customer arrival will be in random fashion. Means no customers will fixed. So different customers came to the bank, for example, came to the bank for different purpose. Withdraw money or deposit money or deposit check or withdraw money in this way. So the arrival will be in random fashion, which cannot be predicted. We can never predict in which time a customer will come because the customer is an independent individual and the service organization has no control over the customer. The characteristics of arrival are shown in the figure. So this is the diagrammatical representation. Here, what is actually arrival? Arrival, nature of arrivals, capacity of the system, customer's behavior. Capacity of the system is limited or unlimited. Customer behavior is bulking, reneging, collusion, jerking. Then size of arrival is again finite population or infinite population. Arrival time distribution, that is constant or random. Then size of arrival. The size of arrival to the service system is greatly depends on the nature of the size of the population, which may be infinite or finite. The arrival pattern can be more clearly described in terms of a probability and consequently the probability distribution for inter-arrival times. The time between two successive arrival or the distribution of member of customer arriving in unit time must be defined. That is not the size of arrival. It is of two types, that is a finite and infinite. Inter-arrival time. The period between the arrival of individual customer may be constant or may be scattered in some distribution fashion. Most queuing models assume that the sum inter-arrival time distraction applies for all customers throughout the period of study. It is true that in most situations that service time is a random variable with the same distribution for all arrival. But cases occurs where there are clearly two or more classes of customers, such as a machine waiting for repair with a different service time distribution. Service time may be constant or random variable. Then capacity. So capacity is limited or unlimited. Capacity of the service system in queue context, the capacity refers to the space available for the arrivals to wait before taken to service. The space available may be limited or unlimited. When the space is limited, the length of waiting line crosses a certain limit. So no future units or arrivals are permitted to ensure that the system will some waiting space becomes vacant. This type of system is known as system with finite capacity and it has its effect on the arrival pattern of the system. For example, a doctor giving tokens for some customers to arrive at constant or a certain time and the present system of allowing the devotees for class for darshan at any temple. Customer behavior. What is actually customer behavior? The customer behavior means the length of the queue or waiting time of a customer or the idle time of the service facility. Mostly depends on the behavior of the customer. Suppose the customers are not in a queue, no customers are there. At that time, at the service point, the service provider are sitting idle. Here, the behavior refers to the impatience of the customer during the stay in the line. Customer behavior can be classified as bulking, reneging, collusion, and checking. What is actually the bulking? Bulking means this behavior signifies that the customer does not like to join the queue. Means here, bulking means the customer does not like to join the queue. By seeing the long length of it, suppose you are now ready to join to report in the office, just like every day. Suppose one day you want to take some service from the mechanic on the way of your office. At that time, suppose you are moved and saw there are number of customers are waiting to take the service from the mechanic. So at that time, you just leave that, you are not joining the queue and just leave. That is known as a bulking. This behavior may affect in losing a customer by the organization. Always a lengthy queue indicates insufficient service facility and customers may not turn out most time. For example, a customer who wants to go by train to his destination goes to railway station and after seeing the long queue in front of the counter may not like to join the queue and seek other type of transport to reach his destination. Then like reneging. In case of customers joins the queue and after waiting for certain time losses his patience and leave the queue. This behavior of the customer may also cause loss of customer to the organization. Then collusion. Collusion, in this case, several customers may collaborate and each one of them may stand in the queue. One customer represents a group of computers or customers. Here the queue length may be small but service time for an individual will be more. This may break the patience of the other customers in the waiting line and situations may lead to any type of post case. Then jockeying. If there are number of waiting lines, depending upon the number of service station, for example, petrol banks, cinema theater, etc. A customer is one of the queue after seeing that the other queue length, which is shorter, with a hope of getting the service, may leave the present queue and join the shorter queue. Perhaps the situation may be that other queue, which is shorter, may be having more number of collaboration customers. In such cases, the probability of getting service to the customer who has changed the queue may be very less. Because of this character of the customer, the queue length may goes on changing from time to time. So this is now the queuing process. Then Input to the queuing system refers to the pattern of arriving customers at the service facility. We can see a ticket counter or near petrol bunks or any such service facility that the customer arrives randomly, individually, or in the batches. The input process is described by the following characteristics: nature of the arrival, capacity of the systems, and behavior of the customer. Then size of arrival. The size of arrivals to the size of system is generally depends on the nature of size. Size of the population, which may be infinite or finite. The arrival pattern can be more clearly described in terms of probabilistics and consequently the probability distribution for inter-arrival times, time between two successive arrival, or the distribution of numbers of customers arriving in unit time must be defined. So this is not just size of arrival. Then inter-arrival time. A period between the arrival of individual customers may be constant or may be scattered in some distribution fashion. Most queuing model assume that the sum internal time distractions applies for all customers throughout the period of study. It is true that in most situations that service time is a random variable with the same distribution for all arrivals, but cases occurs where there are clearly two or more classes of customers such as a mechanic waiting for repair with a different service time of distribution. Service time may be constant or random variables. Then the capacity of the service system. In queuing context, the capacity refers to the space available for the arrival to wait before taken to service. The space available may be limited or unlimited. When the space is limited, length of waiting line crosses a certain limit. No further unit of or arrival are permitted to enter the system till some waiting space becomes vacant. This type of system is known as system with finite capacity and it has its effect on the arrival pattern of the system. For example, a doctor giving tokens for some customers to arrive at a certain time and the present system of allowing the devotees at a temple by using the token belt system. Then customers behavior. Customers behavior is one important component. Customer behavior, the length of the queue or the waiting time of a customer or the idle time of the service facility mostly depends on the behavior of the customer. The customer behavior is always depends on waiting time of a customer, the idle time of the service point, service facility, like that. Here the behavior refers to the impatience of a computer during stay in the line. Customer behavior can be classified as bulking, imaging, collusion, and jockeying. Service mechanism or service facility. The time required to serve the customer, to give the serve means what? To give the service to the customer cannot be estimated until we know the need of the customers. Many a time it is statistical variable and cannot be determined by any means such as number of customers served in a given time or time required to serve the customer until customer is served completely. Service facility design and service discipline and the channels of service is shown in the figure and may generally determine the service mechanism. The service mechanism consists service facility design and queuing or service discipline. And service facility design again distributed or divided as single channel and multi-channel. In single channel, we consider two other concept, that is single channel or multi-channel, and for multi-channel we know that is called as single multi-channels. Now queuing service discipline. In the queuing service discipline, there are four terms. One is FIFO, first in first out, LIFO, last in first out, and zero, and service by priority. These are the four criteria in the queuing discipline. Then service facility design. Service facility design. Arriving customers may be asked to form a single line or multiple line, depending upon the service need. When they stands in single line, it is known as single channel. Means one queue, one service point. That is called as single channel facility. When they stand in multi lines, it is known as a multi-channel facility. Suppose there are multiple queue and multiple service point. That is called as a multi-channel facility. Then we discuss about queue discipline or service discipline. When the customers are standing in a queue, they are called to serve depending on the nature of the customer. The order in which they are called is known as service discipline. There are various ways in which the customer called to serve. They are FIFO, that is called your first in, first out, first come, first served, FCFS. Similarly, LIFO. What is the meaning of LIFO? LIFO means last in, first out. Means last come, first served. Service in random order. SHIRO. SIRO. Service in random order. Then service by priority. So these are the different queue discipline or service discipline points. Then we discuss about what is actually fast in, fast out. We are quite aware that when we are in a queue, we wish that the element which comes should be served fast so that every element has a fair chance of getting service. Moreover, it is understood that it gives a good moral and discipline in the queue. When the condition of FIFO is violated, there arises the trouble, and management is answerable for these situations. So this is known as FIFO. Similarly, LIFO. LIFO stands as last in, first out. Means when the customer comes, at last he get the service first. That's why it is called as your last come, first served, LCFS. Service in random order, zero. Service in random order, it indicates that the customer gets the service without any sequential order. In this case, the items are called for service in a random order. The element might have come first or last, does not bother. The servicing facility calls the elements in random order without considering the order of arrival. This may happen in some religion organization organizations, but generally it does not follow in an industrial or business system. In religious organization, when devotees are waiting for the darshan of the god man or god woman, the devotees are picked up in random order for blessing. Sometimes we see that in government offers or offices, the representations or applications are various favor are picked up randomly for processing. It is also seen to allocate an item whose demand is high and the supply is low. Also seen in the allocation shares to the application of the company. Similarly, we discuss about the service by priority. Priority disciplines are those where any arrival is chosen from service ahead of some other customers already in the queue. In the case of primitive priority, the displayed to take it into service. In primitive rule of priority is one where an arrival with low priority is given preference for service that a high priority item. For an example, we can quote that in a doctor's shop, when the doctor is treating a patient with stomach pain, suddenly a patient with heart stroke enter the doctor's staff. The doctor asks the patient with stomach pain to wait for some time or give attention to heart patient. This is the rule of priority. Then we discuss about steady state and transition state. So what is actually steady state and what is actually transient state? We discuss in this slide. The system will settle down as steady state when the rate of arrival of customer is less than the rate of service. A customer arrival time is less and then the rate of service and both are constant. The system not only becomes steady state but also become independent of the initial state of the queue. Then the probability of finding a particular length of the queue at any time will be same. Through the size of the queue fluctuated its steady state, the statistical behavior of the queue remains steady. Hence, we can say that a steady state condition is said to be prevail when the behavior of the system becomes independent of time. Then, transient state. Wing theory analysis involves the study of a system behavior over time. A system is said to be in transient state when its operating characteristics or behaviors are dependent on time. This happens usually an initial stage of operation of the system, where its behavior is still dependent on the initial condition. So when the probability distribution of arrivals on waiting time and servicing time are dependent on time, the system is said to be transient time. So this is the difference between the steady state and the transition state. Then we can discuss one example. For example, a television repairman finds that the time spent on his job has an exponential distribution. It is mentioned in the question with mean of 30 minutes. If the arrival 30 minutes, if he repairs sets in order in which they came in and if the arrival of sets follow a Poisson distribution approximately with an average rate of 10 power 8 hours per day. What is the repairman's expected idle time each day? How many jobs are ahead of the average set? Just write it. Now we discuss the problem here. So first of all, we have to find a television repairman finds that the time spent on his job has an exponential distribution. It is mentioned in the question with the mean of 30 minutes. So we have lambda equal to 10 by 8. Average rate per 8 hour per day. Then 10 by 8 equal to 5 by 4 sets per hour. And mu equal to 1 by 30 into 60 equal to 2 sets per hour. Expected idle time of repairman each day equal to number of hours per which the repairman remain busy in an 8-hour day. Then lambda by mu equal to 8 divided by 5 by 8 equal to 5 hours. That means 8 cancel, that is reverse, and 5 by 8 into 8, that is indicates that 5 hours. Hence the ideal time of the repairman in an 8-hour day will be 8 minus 5 equal to 3 hours. Expected average number of TV sets in the system can be calculated by using a formula, that is LS equal to lambda divided by mu minus lambda equal to 5 by 4. That is the lambda is calculated earlier, that's 10 by 8, that is 5 by 4, slash mu equal to 2, that is 4 slash 2 minus 5 by 4. So if you calculate, you get that is 5 by 3 equal to 2 approximately TV sets. So this is the example 1. Then we can discuss the example 2. On an average 96 patients per 20 hour per day require the service of an emergency clinic. So suppose patients are visit to emergency clinic and the data given here 96 patients per 24 hour. Also on an average a patient requires 10 minutes of active attention. Assume that the facility can handle only one emergency at a time. Suppose that it costs the clinic rupees 100 per patient treated to obtain an average servicing time of 10 minutes, and that each minute of decrease in this average time would cost rupees 10 per patient treated. How much would have to be budgeted by the clinic to decrease the average size of the queue from 1 and 1/3 patients to half patients? So that is the question, and the solution is that we have to first calculate what is the lambda and what is the mu. From the data of the problem, we have calculated lambda equal to 96 divided by 24 into 60, we get 1 by 15, and similarly mu equal to 1 by 10, that is the number of patients per minute. Then we have to calculate P equal to lambda by mu equal to 2 by 3. Then different calculations are there. We have to calculate the average number of patients in the queue. Average number of patients in the queue. That is LQ equal to P square divided by 1 minus P. So 2 by 3 whole square divided by 1 minus 2 by 3 equal to 4 by 3. 4 slash 3. That is, you can calculate the denominator. Then we divide with the numerator value. Then we get this answer. Then Number two, fraction of the time for which there are no patient. That means P0 equal to 1 minus P. That is 1 minus 2 by 3 equal to 1 by 3. When the average queue size is decreased from 4 by 3 patients, the new service rate is determined as LQ equal to lambda square slash means divided with mu into mu minus lambda, or 1 by 2 equal to 1 by 15 whole square divided by mu into mu minus 1 by 15 whole square, where mu is the 2 by 15 patients per minute. Then we calculate the average rate of treatment required. That is 1 by mu equal to 15 by 2 equal to 7.5 minutes. A decrease in the average rate of treatment is 2.5 equal to 10 minus 7.5 minutes. Budget per patient equal to rupees 100 plus 2.5 plus 0 equal to rupees 1.25 per patient. So this is your example 2. Now similarly, we can discuss another example. A telephone user arrive at a booth following a poison distribution with an average time of 5 minutes between one arrival and the next. The time taken for a telephone call is on an average 3 minutes and it allows the exponential distribution. What is the probability that the booth is busy? How much service rates should be increased in order to reduce the waiting time to less than or equal to half of the present waiting time? So this is a question actually. Now we can solve it. The solution is, first we have to calculate the lambda. So given that arrival rate lambda equal to 12 per hour, service rate mu equal to 20 per hour, probability that booth is busy, that is 1 minus p naught equal to lambda by mu, that is 12 by 20 equal to 0.60. Average waiting time in the queue WQ equal to lambda by lambda into lambda minus lambda mu into mu minus lambda equal to 12 divided by 20 into 20 minus 12 equal to 3 by 40 hour. Average waiting time in the system, that is indicated as W, is equal to 1 slash, that means divided with mu minus lambda equal to 1 by 20 minus 12, that is 1 by 8 hours. In case the waiting time is required to be reduced to half, we have Ws equal to 1 by mu minus lambda, that is 1 by 16 equal to 1 by mu dash minus 12 or mu dash equal to 28 per hour. Then hence the increase in service rate should be 8 users per hour. This is known as your quick example, how to calculate the service rate. Then we can discuss the single channel queue or multi-channel queue. For example, during university or college admission, the students go through one counter after another before their admission formalities are complete. In the parallel arrangement, the incoming customer may join the queue of his choice in front of service facility, or he may be served by any service facility. The number of check-in points at the airport is one of the example of the arrangement of service facility in parallel because the customer may check in from any counter. The mixed arrangement is this arrangement consists of service facility arranged in series as well as in parallel. In a hospital, for example, an incoming patient may go to any of the registration windows where he is checked by various doctors one by one. That is Raja, the service process. Then distribution of service time. The time taken by the server from the commencement of service to the completion of service for a customer is known as service time. One of the mathematical distribution often used to describe service time. Distribution is the negative exponential distribution. It has a continuous probability density function of service time of the firm. We can represent it as f of t equal to mu e to the power minus mu t, where t greater than equal to 0. That is, t indicates the time of service. 1 by mu indicates the average time spent serving a customer. And P represents as n service completion in time t. So this is known as the distribution of service time. Now I am summarized some important concepts we discuss in today's class. So we know that the queuing theory, and the queuing theory means actually the queuing problem is identified by the presence of a group of customers who arrive randomly to receive some service. The customer upon arrival may be attended to immediately or may have to wait until the server is free. The service time required to serve the customer is also a statistical variable. The methodology can be applied in the field of business, that is the bank, booking counter, industries, servicing of machines, or government, railway or post office counters. Transportation, that is airport, and everyday life, that is the elevators, restaurants, and doctor's chamber. The queuing model are basically relevant to service-oriented organizations and suggest way and mean to improve the efficiency of the service. Means how you provide a better service to your customers. An improvement of service level is always possible by increasing the number of employees. Apart from increasing the cost, an immediate consequence of such a step is utilized or idle time of the server. In addition, it is unrealistic to assume that a large scale increase in staff is possible in an organization. Queuing methodology indicates the optimal usage of existing manpower and other resources to improve services. It can also indicate the cost implication if the existing service facility has to improve by adding more servers. And as we know that the queuing theory can be applied to a variety of situations where it is not possible to accurately predict the arrival rate of the customer and service rate of service facilities or the facilities to the customer. Then, in particular, it can be used to determine the level of service or the number of service that balance the following two conflicts. That one is cost of offering the service and cost incurred due to delay in offering service. So that's why we need to understand the queuing theory and which is applicable in the business organization to provide a better service to the customers and how the queuing theory works. Then different applications of queuing theory. The queuing theory is applicable in business logistics, banking and finance and telecommunication, project management, emergency service such as fire, police and ambulance. How it works and how involved it may be depends on the complexity of the case involved. Then different parameters of the queuing theory. One is your arrival, number of servers, queue, and the service capacity, and the client population, and size of client population, queuing discipline, then departure process. So these are the different parameters. Examples of queuing theory and different notations and symbols of queuing system. Then queuing models, probabilistic queuing model, deterministic queuing model, mixed queuing model. Then queuing process. Hence, what is the arrival pattern? To understand the arrival pattern, to understand the service mechanism or service pattern, the queue discipline and customer behavior. Then customer behavior. In customer behavior, we understand the pattern and how the customers get the service or takes the service from a queue, and it can be classified as bulking. Bulking means what? The customer does not like or interested to join the queue whenever she saw the long length of the queue. This behavior may affect in losing a customer by the organization. Then reneging. In this case, the customer joined the queue and after waiting of certain time loses his patience and leave the queue. Means a customer visit, stand in a queue and wait for some times, but after so many times of waiting, he leave the queue, does not take the service. This behavior of customer may also causes loss of customers to the organizations. In collusion, in this case, several customers may collaborate and only one of them may stand in the queue. One customer represents a group of customers. Here the queue length may be small, but service time for an individual will be more. This may break the patience of the other customers in the waiting line, and situations may lead to any type of post episode. Then jockeying, if there are number of waiting lines depending on the number of service station, for example, cinema theaters, petrol pump, a customer in one of the queue after seeing the other queue length, which is shorter, with a hope of getting service, may leave the present queue and join the shorter queue to take the service. In this way, we know about the single channel, multi-channel queue, queue discipline, FIFO, LIFO, Shiro, and service by priority. And we know about steady state and transition state. And one example to calculate the expected average number of sets in the system